Hello, Chem 115 students. Let's have a conversation about free energy and how that has to do with spontaneity, including the notions of how it pertains to enthalpy, heats of reactions, entropy, randomness, and overall free energy change. And we'll see how this affects what we're looking at in reactions. So, have you thought about entropy a little bit previously? Entropy is a measure of randomness, and so here's some examples where we need to recall how entropy is described. So if you're looking at iodine as a solid subliming to a gas, is that an increase or a decrease in entropy, as in is the randomness or disorder increasing? Going from a solid to a gas is always an increase in entropy, and so that would be a value of delta S that is greater than 0. The next example of sodium with chlorine reacting together, a sodium solid, chlorine gas reacting together makes sodium chloride, giving off lots of heat. This one is a little bit different because you have two substances combining to make one, and you have in fact 3 moles to begin with, and the result is 2 moles. But more specifically, you have a solid and a gas combining to make a solid. And so each of those considerations, going from 3 moles to 2 moles, or to notice that they're going from solid and gas to a solid, would suggest that you are decreasing entropy. And so this one, the change in entropy is going to be less than 0. The third example on this page shows you the reaction of nitrogen with hydrogen to make ammonia. Here we have 2 gaseous substances making another gaseous substance. On the left side we have 4 moles of gas, and on the right side we have 2 moles of gas. Well, looking at numbers of moles, we're going from more moles to fewer moles. So that would be going from higher entropy to lower entropy. Again, that would be decreasing entropy. And when we describe that, the value of delta S is going to be less than 0. When it gets smaller, it's less than 0. Okay, we have a number of examples that are shown with pictures here. Not everybody likes these, so let's talk our way through them and see if it helps you to think about entropy a little bit more clearly. The first box in the top left, we have an orderly set of spheres, which must be representing a solid. And the end of the reaction, we have spread out spheres, so that would be assuming to be a gas. And so if you're going from a solid to a gas, entropy is doing what? Well, is it getting more random? Sure. And so in that case, the entropy change is going to be greater than 0. We don't have to know the number, we just know that it's increasing. Example number 2, the top right. We have a nice orderly pile of little spheres, so that would be a solid. And as a course of the reaction, apparently, it turns into 2 different little colored spheres. One is gold and one is blue. And so you have gas molecules of some kind there. We don't have to know. And so going from a solid to a gas is definitely an increase in entropy. So delta S is greater than 0 again. Third example on the bottom left. We have on a set of spheres here that are spread out widely and not in any particular order, so that represents a gas. And the gas is being converted to something else that's all at the bottom of the box, and so this must be a liquid because they're not orderly. So if a gas is being converted to a liquid, is it getting more orderly? Yes. The molecules are closer together, they're less randomly arranged, and so in this case the entropy value is decreasing. The randomness of the system is decreasing. Last example, we have 2 double red atoms in a molecule and double blue atoms in a molecule, so we could call that A2 and B2 perhaps, because there's a number of possibilities that would pertain to that here. And so A2 and B2 react in some fashion to form a new molecule. And the new molecule on the right, let's call A red. That would be A2B. That could be something like hydrogen and oxygen making water. There are other ideas as well. And on the left, these appear to be gaseous as far as we can tell, but that's not the only consideration. And on the right, probably also. We're not looking any different here. So it's not necessarily whether we've made a gas or from some other state, but what else can you consider to decide whether entropy is changing? Because we're looking for a change in entropy here. And on the left side, we have 1, 2, 3, 4 A2 molecules. And how many B2? It looks like same number. So there's 4 there as well for a total of 8 moles of reactants. And on the right side, we have how many then in the products? Well, it turns out there's some extra B2 molecules left over, but whatever the case, there's 4 A2 molecules, and A2B, sorry, and then 2 B2 molecules left over. Well, if you look at the total number of moles, that gives you a better clue here. In this case, we have a total of 6 on the product side, 6 moles, and we began with 8. And so in entropy considerations, we would deem this to be a decrease in entropy because you have fewer moles of product than you do of reactant. So entropy is decreasing, it is going to be less than 0. These examples do take some thinking and getting used to, so give yourself some time to think your way through them. We'll use some more in a little bit. Okay, so why do we care about entropy? Entropy is used to describe, or in calculating, what we call free energy. Free energy, which is kind of sounds like a misnomer in the 21st century because you know you have to pay electric bills and pay to put gas in your car. But free energy has to do with chemical reactions, and it considers not only the heat of reaction, which we call the enthalpy change, delta H is enthalpy, the heat change, and it considers the temperature, which for these calculations will always need to be in kelvins, as well as an entropy change, the change in randomness. And so delta G equals delta H minus T delta S because they told you so. But it's how we determine spontaneity. Whether or not a reaction is spontaneous can be determined simply by knowing the value of delta G. So why do we will describe how delta G is determined and the things that go into it, but the factors that are shown in this equation are what we're going to be working with. All right, these will apply to both physical and chemical changes, and we'll look at some examples of what is used, how delta G is used or determined. So one of the things you have to remember for sure is that temperatures will always be in Kelvin, in other words, absolute temperatures, and that the units on delta S, the entropy changes, are typically very small. They're going to be measured in calories, and values for delta H are generally much larger. They're going to be in kilocalories. So the value for T delta S in this equation is going to generally be small unless the temperature gets really big. So it depends on what your temperature is, how large that factor is that's being subtracted from delta H. So if that value overall is small, that means that delta G generally is similar to delta H, unless your temperature and delta S are much larger than some other, than just by guesses. So typically, delta G and delta H have the same sign, but that's not a guarantee. The bottom line is this. If delta G is less than 0, a negative value, the reaction is described as exergonic, which is analogous to exothermic, but more specifically, spontaneous. So negative values are described as exergonic reactions, and the reactants are going to have a higher energy than the products. If the opposite is true, if delta G is greater than 0, other way around, now we're talking about a reaction that's endergonic, which is analogous to delta H being greater than 0 for endothermic reactions, and these are the ones which are not spontaneous. So if you can find a delta G value, you'll know whether something is spontaneous or not. And now, in the same sense, the way we think about reactants and products energies, for the endergonic reaction, the products will be the ones that have a higher energy. So it's kind of going uphill in reaction energies, something like the endothermic reactions we've seen before. The exergonic reactions are going to have an energy barrier, but they end up at a lower energy for the products. Now, these are not very sophisticated diagrams, but you've seen some like this, and these can be used for free energy considerations just as much as they're used for heat energy changes. Okay, so here's another one. Can we apply these ideas of free energy and so forth to this particular example? Again, I know it's not your favorite thing, but let's work our way through these picture diagrams. We asked, and this is straight from the textbook as this number would suggest, to determine the signs of delta H, delta S, and delta G for the spontaneous conversion of a crystalline solid to a gas. So they're being nice, they're being real obvious for you. They're telling you it's a solid, and it's turning into a gas. Well, we've done something like this a few minutes ago. So what was delta S? When you go from a solid to gas, increasing or decreasing? Is it getting more random? Certainly it is. So delta S is greater than 0. If you're turning a solid into a gas, that gives you all you need to know to think about delta H. So do you have to warm up something to go from a solid to a gas, or do you cool it off? Well, so last I checked, that would be something that needs to be warmed up, and so you're adding heat, and the heat change is therefore greater than 0. Adding heat, endothermic process. Now, what about delta G? The spontaneity of this process. How do you know whether the solid goes to a gas spontaneously or not? Well, in this case, it seems like a trick question, but you just go back to the information provided in this case that tells you it's spontaneous. And so delta G this time is less than 0 because that is always true when a reaction is spontaneous. That's all you have to say. We don't need values and numbers here. We're just looking at signs on these particular quantities. All right, so let's do another one. This is a different kind of thing where we're going to do some calculations, and I'll talk you how you through a calculation with delta G. So for melting ice at a temperature that is below the freezing point and determining whether or not the process is spontaneous. So minus 10 Celsius is certainly below the freezing point of water. And so the freezing point of water has a delta H value. This would be the heat of melting or heat of fusion. And if you looked at Chem Activity 25, you saw that value, or that described a little bit. The heat of fusion for water is shown here as 1.44 kilocalories per mole. And that's part of what you need to know because delta G equation requires delta H. The other piece you have to know for this is the entropy value for that process of melting. And for this one, we have a value of kilocalories, 5.26 kilocalories per mole times Kelvin. That's the funny units that you get for delta S. And so in order to come up with delta G, you use those two values in the equation that we've seen a moment ago. Delta G equals delta H minus T delta S. Plug in the numbers, but pay attention carefully in this case to the units because the heat values, the heat values are going to have a larger value unit on them than the entropy values, kilocalories compared to calories. So putting in numbers, delta H is the 1.44 kilocalories per mole, and the temperature, minus 10 Celsius. Well, make sure you pay attention and use Kelvin, or you'll get something goofy because then it'll change the sign too. But minus 10 Celsius is 263 Kelvin, and multiply that times the entropy value. Well, putting it in your calculator, hopefully if you pause the video here for a moment, you can do your own calculations. And when you do, you can come up with these values. So the first number you don't do any calculations, but the second number is a significant number of calories per mole. Well, in order to complete the calculation, we're going to have to convert one of these. The simplest one to convert in this case might be, it depends on how you think of them, might be to convert the kilocalories. So let's think the kilocalories in terms of calories. So if you have 1.44 kilocalories, it's 1,440 calories. And remembering that 1 kilocalorie is going to be the same thing as 1,000 calories. Kilo, anything is always 1,000 of something, or 10 to the third. Most of you will prefer to think of this in terms of 1,000, I suspect. So if there's 1.44 kilocalories, that means there's 1,400 of them. Now you can do the subtraction step, and the answer is, well, what is it? 1440 minus 1383. And if your math serves you well, you have an answer here, and it should be 57. Oops, backwards. Oh, I'm sorry. 57 calories per mole. So, is this process spontaneous or not? Well, remember this is delta G we just calculated, and delta G is always determines whether something is spontaneous. If the value is positive, the process is not spontaneous. Well, that makes sense. At minus 10 Celsius, does water melt spontaneously? I don't think so. It needs to be warmer. So let's do another calculation to compare this one. Or we could, but I'm not doing it right here. Let's see. If you chose to recalculate this value of delta G at a temperature greater than the melting point, say for example 10 Celsius, you could determine whether or not that would be spontaneous. But if you think about it for a minute, you can probably predict that if your temperature is greater than the freezing point, melting point, then the process of melting should be spontaneous. But you can do the calculation using exactly these same kinds of numbers with a different temperature and verify it. Let's do a couple other examples with picture diagrams. And no, they're not your favorite, but let's think our way through them. First thing we're going to look at is a reaction of A molecules, the spheres, turning into B solid and C as a gas. And we're trying to determine the sign of delta S. Well, if you're going from solid to a solid plus a gas, well, is that a change in entropy that's positive or negative? Is it getting more random? Anytime you include a gas when you didn't have one before, that's certainly an increase. So delta S is greater than 0. The trick now is to decide whether the reaction is spontaneous at all temperatures, non-spontaneous at all temperatures, or spontaneous at some but not all. What can you do to determine this? Well, a couple things we have to look at. First of all, the equation is this. Delta G determines spontaneity, and it's going to be based on the value of delta H, which is not explicitly shown here. Subtract from that temperature times delta S. All right, so depends on what delta H is, and chances are you're going to have to add heat to take a solid and break it apart to make a solid in another gas. So let's presume that delta H is greater than 0. If so, this value for delta H in this equation is positive, and then temperature being in Kelvin should always be positive, and delta S we just said was also positive. So if you subtract a positive value from the delta H being also positive, the overall calculated value may or may not be positive depending on the size of the temperature. So if you have a big enough temperature, the second quantity, T times delta S, will end up large enough eventually to overtake the size of delta H. So this tells us that negative values of delta G can be determined if you have its high enough temperature. So it's spontaneous at some temperatures, but not at others. So that's one of these logic questions that you can work with here without any numbers whatsoever, but you can get an idea based on the signs of delta H and delta S. So things to remember. The reverse of a spontaneous process is always non-spontaneous. So if one process has a delta G that's negative, its reverse will be positive. And any process that's non-spontaneous will require an continuous external influence to keep it going. We like to think that spontaneous processes are exothermic. Commonly they are, but not always. If you have ice melting, as long as it's warm enough, that can be spontaneous, but it requires the input of heat, so that's endothermic. And perfume dissipating, going from a solid to a gas, or maybe liquid to a gas, that is also endothermic. But again, if your reaction conditions are warm enough, that will indeed be also spontaneous. So not all spontaneous processes are exothermic, even though we're tempted to think that on occasion. So, only a few more thoughts here. Nope, that's all I needed to say for this session for our Integrity recording. Good luck working on your homework, and we'll have just another recording later to talk about calculating heats of reaction.